So this is DeMoivre's theorem. So DeMoivre's theorem. For any complex number in polar form. So we're going to take complex numbers, change them to polar form, just like we did in the last lesson. And positive integer n, we can take that complex number to a power like 10 by taking r to the 10th and multiplying theta by 10. Because of the cyclic nature of cosine and sine, if I give you an angle, just give you some angle on the somewhere along the unit circle, then it's going to multiply it and give you another angle somewhere there on the unit circle that you can figure out, and then change it back into rectangular form. So very powerful. It allows us to take something like, you see where this baseball is? This guy's going, what? Negative root 3 plus I to the 6th? I really wouldn't want to do that by hand using distributive property. It would be a mess. And the probability of making a mistake would be high. So we're going to change that to polar form, then take it to the 6th using this theorem, and then change it back to rectangular. So the first 4 on your homework, I just started like this. This is just getting familiar with the formula, and then this is really why we would even need to use the formula. So this one, you'll see there is a number written in front of this, so we assume that r is 1. So in this case, r is 1. This represents z. This entire number is z. And so using the formula, if r is 1, and I'm taking it to the 5th power, it would be 1 to the 5th, and then cosine. And according to the formula, we just multiply the power by the angle. So it would be 5 times 7 pi over 10 plus I sine of the same thing. 5 times 7 pi over 10. This is where it's really nice to use the shorthand because the angles are the same. So 1 to the 5th is still 1. We can drop that if we want. And we have cosine of 35 pi over 10 plus I sine 35 pi over 10. And if I simplify that, that's 7 over 2. And so we have cosine of 7 pi over 2 plus I sine of 7 pi over 2. If you'd like to, you can think about what this is equivalent to on the unit circle between 0 and 2 pi. 7 pi over 2, if you think about it. So 4 pi over 2 would get you back where you started. You with me? So this is actually equivalent to cosine of, if I'm back where I started, or think of it this way, 7 over 2 equals 3.5. So if I take out minus 2, I end up with just 1.5 and then slap on a pi, or 3 pi over 2. So this is the same as cosine of 3 pi over 2 plus I sine of 3 pi over 2. And then if I want to change that back to rectangular form, I just need to substitute in whatever cosine of 3 pi over 2 is. So cosine of 3 pi over 2 is 0 plus sine of 3 pi over 2 is negative 1. So I have I times negative 1. So this equals negative I, and you can box it. So this number, which has a rectangular form. We didn't start with it in rectangular form, but this number in rectangular form to the 5th can be changed to polar form. Here it is, and then we can take it to the 5th power, and we get negative I. So that's what you would get if you were to expand that thing out, replacing I squared with negative 1, combining anything with an I attached to it. You've done stuff like this before, but not changing it to polar first. All right, B. This is to the 12th power. To the 12th power. So it's the 4th root of 5 cosine pi over 18 plus I sine pi over 18 to the 12th. So according to the theorem, we'll have the 4th root of 5 to the 12th power. And then in parentheses I have cosine of 12 times pi over 18 plus I sine of the same thing. 12 times pi over 18. Fourth root of 5 to the 12th. Just to refresh your memory. This number, this root, fourth root, can be written as a fractional power. Remember that? It goes like this. We have 5. Just like roots are under the ground, the root is the bottom of the fraction. Just like roots are under the ground. So it looks like this. 4 is down here, 12 is up here. Now we see exactly what that is. It's the same as 5 to the third power, right? So if you think of this in terms of a rational power, write it as a ratio. It's the root on the bottom, power on the top. That'll be 5 to the third. And then here I have cosine of 12 pi over 18 plus I sine 12 pi over 18. And then we're going to simplify it. So the 5 cubed times cosine 2 pi over 3 plus I sine 2 pi over 3. 5 cubed is 125, so I have 125. Cosine of 2 pi over 3 would be, cosine of 2 pi over 3 would be right up here. So you know what the cosine would be here? Negative 1/2. And so this is negative 1/2 plus I sine. Is our picture again? Sine going to be up here. Root 3 over 2, yeah.
You don't need the sign part though, do you?
No, we don't. We need to replace that. So it's I times root 3 over 2. And then we simplify it. So this equals negative 125 over 2 plus 125 root 3 over 2. And that's your final answer, and with an I attached. Rewrite that. So it'll be negative 125 over 2 plus 125 root 3 over 2I. All right, so now let's take a complex number in rectangular form and go through the whole process. We're going to change it to polar. Maybe draw a picture here. Negative root 3 plus I would be somewhere over here. So negative root 3, so we're farther out than we are up. So it corresponds to this right here on the unit circle. So can you tell me what the, first of all, what is R? I want to change this to polar form, so figure out what R is. Let's see. So we have negative root 3 squared. It's going to be 1, I think, in the next one here. This one's going to be 2, because that'll be 3 plus 1 is 4. So that'll be 2. So R is 2. So this is going to be equal to 2. I'm going to put bracket around it, because all we're going to do is substitute in polar form for negative root 3 plus I, and then take that to the 6th power. So it's cosine of, what's the angle over here? Can you tell what the angle is from the picture? It is 5 pi over 6, yeah. So it's cosine 5 pi over 6 plus I sine 5 pi over 6, all to the 6th power. So we're taking that number in polar form now to the 6th. So now we can use DeMoivre's theorem, which says take R to the 6th, 2 to the 6th, and multiply 6 times each of the angles. So take and multiply 6 times each of those angles. 2 to the 6th is 2 to the 5th is 32, so 2 to the 6th is 64. And in parentheses I have cosine of 5 pi. 6's cancel out. Plus I sine 5 pi. So 64 times cosine of 5 pi. So we go around once, twice, and then halfway around. It's going to be right here. A -1 and plus I times 0. So this is just -64. So if you can believe that, this thing taken to the 6th power would be equal to -64. So that tells me that all the terms with i's attached get canceled out. I squared get replaced with -1. You end up with just a whole number. Well, an integer. That's a whole number, 64, -64. All right. This one right here, I don't know if you can tell, but do you recognize these ratios? Do you know then what the radius would be just based on the fact that we recognize those ratios? Yes, these are right on the actual unit circle. They are some radius that's different. They're right on the unit circle. So they have a radius of 1. If you were to square each of these, you'd get r equals 1. So this one, if I rewrite it, it's going to be 1. That's the radius. And then, might need a picture here. Root 3 over 2 and -1/2 might be right about there. So root 3 over 2 out, -1/2 down. Can you tell what angle that is between 0 and 2 pi? 11 pi over 6. So it's cosine 11 pi over 6 plus I sine 11 pi over 6. And we're gonna take that to the power of 10. So I'm gonna put brackets around this thing. Brackets around that thing and take it to the 10th power. So 1 to the 10th. And then I have cosine of 10 times 11 pi over 6 plus I sine of 10 times 11 pi over 6. So I'm multiplying the 10 by each of the angles and taking r to the 10th. So 1 to the 10th is just 1. And then this one right here, this would be, if I simplify it, that's 5. That's 3. So it's 55 pi over 3. So I have cosine 55 pi over 3 plus I sine 55 pi over 3. So we got to figure out what angle 55 pi over 3 corresponds to. Is it 2 pi over 3? So the way I think about it, how are you thinking about it to get it? Okay, I would just think about this as a mixed number maybe. So 3 goes into 55. 1's 25. So it goes once into here, once into 5 with 2 left over. It goes 8 times into 25. So it's 18. Would be 54 and 1/3 pi. So the 18 pi is going to get me right back where I started, right? 18 pi, it's an even multiple of pi. So this is really equivalent to just, you're close, but it's equivalent to just pi over 3. So this is the same as cosine
pi over 3 plus I sine pi over 3, which equals, cosine of pi over 3 is 1/2, plus sine of pi over 3 is root 3 over 2I. That is your final answer there. Alright, so that's just an extension of taking complex numbers to powers. It's an extension of multiplying and dividing, so it's an extension. You're just multiplying it several times. Alright? So nth roots for each positive integer n, the non-zero complex number z equals r cosine theta plus I sine theta, has exactly n distinct roots given by the following formula here. Nth root of r. We'll break this down. It's not as scary as it looks. It's really just the same as the theorem I had at the top of the notebook. It's just that there's more than one answer when you're taking roots. It's like when I have x squared equals 9, how many solutions are there? Right? X squared equals 9 has which solution? 2, 3, and negative 3. Same idea here. We're going to have the nth root. There could be 4 solutions if it's a fourth root, 3 solutions if it's a cube root. So really the way to think about this is it's DeMoivre's theorem, but with rational powers or fractional powers. You're still going to take r to that power, like we did in DeMoivre's theorem, and you're still going to multiply that power by the angle, except that you have to consider that there could be, that's what the 2k pi over n part is, there's going to be as many as n roots. So you have to plug in k equal to 0, 1, 2, up to n minus 1. So if you're finding fourth roots, you're going to plug in 0, 1, 2, and 3 and get the 4 different answers for that. That's the only difference between this and DeMoivre's theorem. It's really the same thing. I'll show you what I mean. It is. It's a little bit of work. It can be to just plug it in, but it's not hard to plug in 0. And when you plug in 1, all you're going to be doing is adding 2 pi over n to it. It's kind of like what we did when we were graphing the roses, and we were finding the starting point for the petal, and then we would find the increment. That's what you're doing here until you get back to where you started. So it's really similar to that. Okay. Sometimes you can do it without really having to plug in 0, 1, 2. You'll just see what the increment is. You can tell what it takes to get back to where you started. All right, so just find the cubed roots of 8 cosine pi over 10 plus I sine pi over 10. Leave in polar form. So we're starting with one that's already in polar form. We're going to leave it in polar form. That tells me that when I come up with the 3 different roots, they probably have angles that are not ones that we know as special right triangle angles, okay? So here's how I would think about this. You can write this out. It looks like this. 8 cosine pi over 10 plus I sine pi over 10. That's the number. And what we want to do with that number, it's kind of awkward to write it in radical form. But what we mean by cubed root is to take it to the 1/3 power. You with me? The cubed root means 1/3 power, and that's a little less awkward than trying to write the third root of that polar number. Okay. And actually, I have to be honest with you, as you're as we're thinking about calculus, rational powers are better than writing them in roots. And that's because of one of the formulas that you'll learn for both integration and differentiation. It's better to have it in that form. So you'll see when you get into that next year. So now I can just apply DeMoivre's theorem, really. What does DeMoivre's theorem say to do if I have this polar number to a power of 1/3? What do I do with the r? Take it to that power, right? Okay, so that's the same. So we have 8 to the 1/3. And then DeMoivre's theorem says to do what with the power and the angle? Multiply them, right? There's one little addition here. I'll show you what that looks like. So it goes like this. Cosine of 1/3 times pi over 10. Okay, that's what we would do in the previous problems. But I have to consider that there's more than just one answer. There's actually, how many of them? In this case, more than that, 3, yeah. Square root, there'd be 2, cube root 3, 4th root 4. So I have to write here plus 2k pi over 3. So I have to plug in 0 to get one answer. That'll just be this, like we'd get in DeMoivre's theorem. But then I have to also plug in 1 and then 2 and get the next 2 values to get me back to where I started. If you think of this as a circle, you're going to start at whatever angle this is and then have a common increment that gets you back around to the equivalent angle of this, but 2 pi radians farther along. So plus I sine of the same thing, 1/3 times pi over 10 plus 2k pi over 3. This is where it's really nice to write the shorthand, because now the angle has more to it to write. So I would encourage you to use the shorthand. All right. So 8 to the 1/3. I picked 8 for a reason. It's 2, yeah. So we have 2, and then we have cosine of pi over 30 plus 2k pi over 3 plus I sine the same thing, pi over 30 plus 2k pi over 3. So that's cleaned up for us. So now when k equals 0, okay, what's my answer in polar form when k equals 0? Just pi over 30. So we'll just write it as 2 cosine pi over 30 plus I sine pi over 30. That's a 30 there.
What is this short thing?
Cis, yeah, you could write it as 2 cis pi over 30. And actually, I would encourage you at this stage up here, right up here, is you could write it in cis form then, because like I said, the angle expression is so long, we don't really want to write that twice. I don't want to. But I don't know if we're used to polar form enough yet to start moving into the shorthand. Okay, so that's one answer. What about if k equals 1? Then we have 2 cosine pi over 30 plus, if k is 1, this will be 2 pi over 3. And then plus I sine of the same thing, pi over 30 plus, it's hard to see, 1. Plus I sine of the same thing. So 2 pi, 2 times 1, pi over 3. Need this. let's try it one more time here. Pi over 30 plus 2 times 1 pi over 2 plus I sine pi over 30 plus 2 times 1 pi over should be over 3. And remember is 3 in this one, so this should be over 3 up here. So what does that equal? So we have 2 cosine of, you have to take pi over 30 plus 2 pi over 3. I know you'll love this. How do we add pi over 30 and 2 pi over 3? Pi over 30 times, 2 pi over 3, you got to multiply top and bottom by 10. So that's actually 20 pi over 30. So I end up with cosine of 21 pi over 30 plus I sine of 21 pi over 30. You could simplify it. I would actually encourage you just to leave it like that. Another way to think of this is 2 cis 21 pi over 30. You can actually get the last one just by looking at the increment between the first two. So when k equals, this will save a little time, k equals 2, I went from pi over 30 to 21 pi over 30, so I added 20 pi over 30, right? I guess what I'm going to do, increments the same, it's just like with the rows. So add another 20 to this guy, and that brings you up to 41 pi over 30, so you can skip that calculation step. So it'll be 2 cis 41 pi over 30. And if I added another 20 pi over 30 to 41 pi over 30, I would be at 61 pi over 30, which is equivalent to 1 pi over 30. So as soon as you get these first two, and this is helpful when there's more than, when there's 3 or more roots. As soon as you get the second one, you have the increment, you can make sure you get back around to where you started, okay? Because now we're going to be 4th root. That's probably as much as we'll do it.
So you can't simplify 2 cis. 2 cis. You're 7.
You could, 7 over 10, yeah. The reason I was leaving it at 21 pi over 30 was so that I would easily see the increment is 20 pi over 30, already in a common denominator, to add another one to it. And I'm fine with you leaving the angle without simplifying it. But yes, you could. It's just easier to see this way. And then we do a 4th root, or actually this is 6 roots of unity. This will help us. We'll get the second one, and then we'll see the increment and just keep counting until we get all the way around. Okay? So, final thing here is, why would we do this? Well, here's an equation. You've solved equations kind of like this, but it was probably x squared plus 64 equals 0, right? And you found that it had 2 complex roots. And that's when you're introduced maybe to the fundamental theorem of algebra that says that we have as many in the complex field, as many roots as the highest power on it. Yeah. It's always interesting to explain. Like with algebra students, before they understand that there are complex numbers, you just have to tell them, well, there are no real roots, but there are still roots. So this has 6 complex roots, and we're going to find those using this process. This is what a course in abstract algebra you would spend time on in Galois theory. It kind of culminates in a graduate course called Galois theory, but finding roots of equations and finding just solutions really to equations. That's what the roots are. So x to the 6 plus 64 equals 0. So what I would do first on this is I would say x to the 6th equals negative 64. And then if I'm solving for x, I would take the 1/6 power of each side. Or
the sixth root of each side. You with me? 1/6 power is the same as the sixth root, but I've told you that it's probably better to go in terms of rational powers. I think you'll find that more useful. So this is negative 64 to the 1/6. And so we can use DeMoivre's theorem on this, or this formula up here, to find all 6 answers to this. There are 6 of them. What do you think the first step is we're going to take? What did we do with the baseball one up here? Or let's see, where's the baseball one? Yeah, baseball one, up higher. What did we do with it first? We did, we graphed it, So we could graph this one with the purpose of what? Getting in polar form. That's the whole purpose of graphing a point. So yes, we could graph this point, and as a matter of fact, let's just draw a graph here. Negative 64 would be way the heck out here, right? There it is. Graphed it. That makes it life a lot easier. What is R based on that graph? Okay, theta is pi, yes. What's R? 64. So R is 64. Good. I like the picture method. Negative 64. Remember, this is the real axis. This is the imaginary. This is just the real part of the number. It's negative 64, so I've gone out 64 units to the left on the real axis. And where does that locate me? Well, pi radians around. So, of course, if you couldn't do that, you'd have to use the formula. R equals square root of a squared plus b squared, and so forth. Theta equals inverse tangent of y over x. Okay, so this is x equals, let's change it to polar form here. You said R was 64. Put brackets around it. Cosine of pi plus I sine of pi to the 1/6 power. Yeah. Good. Okay, so now we have our solution in polar form. Now let's apply the formula. So x equals. Let's not lose sight of what we're doing. We are solving an equation. It's just an equation that has complex valued solutions, right? We're solving for x. How many solutions will there be? 6. Yeah, it's a fundamental theorem of algebra. Just the fact that it has the word fundamental in it tells you it's important. It is. Fundamental theorem of algebra says there will be 6 of them. So here we go. It's 64 to the 1/6. And then we have cosine of 1/6 times pi, or pi over 6, plus I sine of 1/6 times pi. So 64 to the 1/6 would be 2, right? All right, and then we have, well, let's just rewrite it. Cosine pi over 6. Now, one thing I forgot to put in here is I should have plus 2 pi k. That actually might work out okay because it just makes it simpler. You can see the connection here between this and DeMoivre's theorem when you don't attach that. But let's go ahead and attach it now. Plus I sine of the same thing. Pi over 6 plus 2 pi k over 6. Okay. So now, what we'll oftentimes do, before I put an equal sign there, is just make our 6 cases. K equals 0. What is that going to be? K equals 1. K equals 2. So go ahead and list them all out. We're going to use patterns, though, to make this easier on us. That's what we like to do as mathematicians is if we see a shortcut, we'll take it. Mathematicians are lazy sometimes. Well, not really. But if we can find a shortcut, we'll take it. So what's the first one going to be here?
Pi over 6.
Yeah, pi over 6. So I have 2 cis pi over 6. And we're going to use our shorthand here. And it's kind of like in science class. Our equation was in rectangular form. So we're going to want to have our answer in the same form. So okay. So this is going to equal 2 times, what's cosine pi over 6 equal? Yeah, root 3 over 2. Plus I times 2 times 1/2. Okay? Which equals root 3 plus I. So there's the first one, root 3 plus I. Okay, the next one is going to be 2 cis. Okay, let's do the math here. We're going to add, put a 1 in here. 2 pi over 6 plus pi over 6 gives me 3 pi over 6. So I have cis, and I am going to leave it as 3 pi over 6 for the reason I mentioned before. Leave it at 3 pi over 6. So this would be 2 times, what's cosine of 3 pi over 6? 4 pi over 2. 0. Plus I times 2 times 1. And so that ends up equaling 2i. So another answer to that equation is 2i. Okay, let's not lose sight of what we're doing here. Go back to the original. What does this mean? If I plugged in 2i here for x, what would I get? What would I have to get if this equation equals 0? I'm finding solutions for x. This has to equal negative 64. If I plug in 2i here, it's got to equal negative 64. That's what I'm saying. I'm solving this equation, right? I know it's weird. We have i's attached. But the principle is the same, right? If I plug in root 3 plus I up here, what am I going to get? Negative 64. So that when I add it to 64, I get 0. Yeah. Good. So k equals 2 is going to be 2 cis. Okay, what was the increment from here to here? Okay, so what do you think we add to this? So this would be 4 pi over 6, which is like adding another 2 pi over 6 to it. So here's what I'm saying. Once you have the increment, you're ready to go. We can fill the rest of this out. It's 5 pi over 6, and there's a built-in check even. This is 2 cis. What's the next one going to be? 7 pi over 6. And where should I end here ultimately? Yeah, something equivalent to pi over 6. So I shouldn't say it's the one before that, but if I were to go one more, I'd get back where I started. So 2 cis 11 pi over 6. Okay, here's the check. If I went one more, I'd be at 13 pi over 6, which is equivalent to 1 pi over 6. So I've done it correctly. Okay, it's like, just picture that rose. The rose petals are going all the way around, and you've just overlaid the first one you started with. Okay. All right, you're going to see some other patterns here as we go. What's cosine of 5 pi over 6? Yes, negative root 3 over 2. Plus I times 2 times sine of 5 pi over 6 is 1/2 equals negative root 3 plus I. Starting to see some patterns here. Well, not really. Maybe. Got this guy, we got this guy, we got this guy. Let's see what comes next. Okay, what's cosine of 7 pi over 6 can equal? Also negative root 3 over 2 plus I times 2 times, this time, negative 1/2. I bet from this point you could fill out the rest. Watch this. This is equal to negative root 3 minus I. So, how do solutions to
Quadratics, or this could be extended to quartics, or I don't know what, sixth roots. How do the solutions come when they are complex valued solutions? What forms do they come in? They do. So they do. If I had x squared equals negative 64, I would get 8i and negative 8i as solutions, right? Remember conjugate pairs?
This is a conjugate pair right here. So what's at least one other solution I'm going to have up here? Yes, Jess.
Square root of 3 minus I.
Yeah, good. And what's the other one I'm going to have up here?
Negative 2i.
Good. Very good. So we have 2 cosine of 9 pi over 6 would be 0. Plus I times 2 sine of 9 pi over 6 would be negative 1. So there's our negative 2i, just as you observed. And then finally, 2 times root 3 over 2 plus I times 2 times negative 1/2. And here comes the other conjugate, root 3 minus I. So they come in conjugate pairs. You could probably save yourself some work once you see 3 different, like if you're looking for 6 solutions and you see 3 different ones, just take their conjugate to find the answer. That's it. We just solved an equation that looks simple at a glance, right? X to the, what to the 6 plus 64 equals 0. If I hand it to other students, they go, oh yeah. Except it just took us into a new realm here, the complex number field. Just something that seems so simple. You guys heard of Fermat's last theorem?